Morning. There's some more seats up front. If anybody wants to take it. So, Mr. Stan, if you want to come in front, please feel free. So, probably since it's 9, I think, and we have a good house full, and I know there might be some others trickling. Let's get started. Morning, everyone. Thanks for being here for our Coulter seminar series. Probably close to finishing up. We have a few more in April, so I wouldn't say this is the last one. But so here we have Dr. Sergio Fantini. He's a professor of biomedical engineering at Tufts University, and he's also the interim chair of the department. And he's the principal investigator for a nice, smiley-looking lab, which is DOIT, or Do It. And I just got to know, I like the way we broke it down, but it's also called as the diffuse optical imaging of the tissue. And his research is mainly focused on non-invasive diffuse optical techniques to assess both cerebral hemodynamics, measure the cerebral autoregulation, perform functional imaging of the brain, and quantify tissue blood flow and oxygenation. His research has resulted in about 120 plus peer-reviewed publications and 13 patents. He has co-authored a book, actually I use it extensively for all my research students as well, is with Professor Sergio from Boston University, and the textbook is Quantitative Biomedical Optics, which was published in 2016. He's a fellow of Optica, which is formerly known as the Optical Society of America, SPIE, and AIMB. So I'd like to welcome Dr. Fantini. He loved the weather of Miami, coming from Boston. So thank you for being here.
Thank you for the nice presentation, for the invitation. Thanks for the department, and I look forward to the visit and to meeting many of you. So yes, I'm from Tufts University, much colder part of the region. I always like the opportunity to come back here. I was saying that I have several friends who after a few years I said I had enough. I'm moving to Florida. Some of them are tennis players, so finally I can play tennis all year round. And yes, that's the lab, the diffuse optical imaging of tissue lab. This logo took full academic year of ideas from all the students and members of the group. And lots of the things I will be talking about today are encoded here. But so what I will be talking about is this diffuse optical approach to study biological tissue, and in particular the emphasis in this talk will be on the human brain. So I'll try to give a broad overview, some historical introduction, given the broad area of expertise in the room. And then I will talk about a couple of special activities in the group on coherent hemodynamics and dual slope techniques, and I'll describe what they are and how they're used. But this is so that's a actual view of Tufts. This is the main campus in Medford, and you can see Boston in the background. And these are the two latest additions to the School of Engineering, or at least where the School of Engineering has some of the space. The department is housed mostly in a different building, more historical, vintage building, but these are the two latest additions that we love to have as part of the school. So yeah, this is what I'm going to talk about, just this non-invasive approach to measurements, optical measurements of the brain, and two applications, cerebral oximetry to study oxygenation, and functional near-infrared spectroscopy for functional brain activation. And then identify two key open questions in the field, the characterization of the measured hemodynamics, and how to address the issue of extracerebral tissue contributions, and how these two methods developed in the lab, coherent hemodynamic spectroscopy and dual slope techniques, are designed to address these issues. And then I'll show some applications on the brain, and I do have one slide on skeletal muscle, just for completeness, if I have time when I get there. So this is the basic idea. The idea is to illuminate the brain non-invasively, so just by placing an optical fiber, a light source on the scalp through the hair, and then this light source can have different properties depending on the technique. So near-infrared spectroscopy can be done with continuous wave light sources, they're just constant over time, or in the frequency domain where the intensity, where the power of the light source is modulated. That is the technique used in my lab, and that is what all of the data I will present are based on. And I'll get back to a description of this later. Or in the time domain where the light source is pulsed. It's a short pulse, picoseconds typically, and then there is the time of flight distribution over nanoseconds as light propagates into tissue. And then diffuse optical tomography to obtain images, and more recently diffuse correlation spectroscopy has been used to study blood flow. But the emphasis here would be on frequency domain near-infrared spectroscopy, and then at the detection side, one can have a single optical detector for measurement of the signal at that distance, or you can have multiple detectors for spatially resolved measurements, and this would be the basis of slope measurements. Every time in this talk I talk about slopes, I'm talking about the first derivative of this spatially resolved measurement as a function of distance from the illumination point. So the first question is, how is it possible that you can optically probe the brain? And this is really the answer. In a cloudy day, we are not in the dark. We cannot see the sun, but we're not in the dark. So light, and here I have an example from my hometown, Florence, and from Florence, Italy. The only drawback is that the soccer team, Fiorentina, just lose their team. I haven't seen it win a league in my lifetime, but the town is beautiful. So you have the sun, you have the clouds, and some of the light, if you think of photons emitted by the sun, some of them will be backscattered, and you can see them when you fly over the clouds. Some of them may be absorbed, and some of them may be transmitted. But the transmission is still after the high scattering experience in the cloud. So this really, qualitatively, is a very good representation of the light source we use on the scalp, the scalp and skull layer before you reach the brain. So the point is that if you look at many photons, some of them, which will be the majority, are back reflected, some of them are absorbed in the tissue, but some of them will make it to the brain. And some of those that make it to the brain because of scattering will eventually make it back, and those are the ones that are detected in this technique. So in a more accurate representation-less approach, one optical fiber for illumination, and then one collection fiber maybe 3 centimeters away for detection. And that is the banana-shaped regional sensitivity that forms the smile in the logo for the group. See, there is encoded information in there. And this is actually data we collected a while ago in a study where we did the concurrent magnetic resonance imaging, because this is the structural magnetic resonance imaging. And this is that banana-shaped regional sensitivity obtained more accurately. And here you see immediately one of the key challenges, one of the key problems of the technique. If you want to probe the brain non-invasively, like this, your photons will have to travel through extracerebral tissue. That banana has actually the majority of the sensitivity to scalp and skull, and only a portion of sensitivity to the brain. So whatever you measure will provide information on both the brain and scalp and skull and other extracerebral tissue. So this is a big picture of the history of optical studies on the brain, and these are 4 of the pioneers of the technique. 1977 is when, in this seminal paper on Science, Franz Jobs presented the idea of using near-infrared light to penetrate through the intact skull and probe the brain. Then there were more developments in the 80s, but 1993 is considered the birth year of functional measurements of the brain using light. in that year, 1993, there were 4 seminal papers from Europe, Japan, and the US. And these are the key people behind those papers: Peter Chance, Mamoru Tomura, and Arno Fillinger. And since the year of birth is so well defined, in 2013, Neuroimage had a special issue to celebrate the 20 years of functional near-infrared spectroscopy, and recently Neurophotonics had a 30-year special issue on functional near-infrared spectroscopy. Then there were a number of developments. I'm not really going through them, but they are from developments in basic science, in applications, and most importantly, in the development of commercial systems. There are now a number of commercial systems available for non-invasive optical measurements of the brain. And then they see how I extend the year up to 2052, because that's when Minority Report takes place. How many of you have seen Minority Report? And here it is. Steven Spielberg. So we are in 2002. So this is less than 10 years from the invention of the technique. And then Hollywood was already on top of that. And I think I can play the key clip.
Exactly how all this works. The photon milk acts as both a nutrient supply and a liquid conductor. It enhances the images that each of them receive. We call the female Agatha. The twins are Arthur and Dashiell. We scan by way of optical tomography.
Optical tomography.
That's also on the entire length of the headgear and are reread after absorption of the brain tissue. In other words, we see what they see.
In the movie, these people were able to visualize events that happen in the future. But how do you see those events from their brain? By way of optical tomography. I was in the movie theater where it was out. I stood up in the theater and said, "That's what I do every day." So we are not quite there yet. That's 2052. But I'll give you a sense of what we can do and why there are reasons to believe that this may be out of reach for this technique, but who knows? So one application is cerebral oximetry. And again, there are a number of commercial devices that implement cerebral oximetry. The idea here is to look at the absorption spectra. The near-infrared region, 650 to 1050 nanometers, is dictated by the fact that outside of these regions, you don't have enough penetration depth to study thick tissues and to reach the brain non-invasively. So the key absorbers here, so I'm really not going into all the details of these chromophores. The key ones are oxy and deoxyhemoglobin. Hemoglobin is the protein in blood that picks up oxygen from the lungs and delivers it to tissue. The key is that optically, the absorption spectrum of hemoglobin when it binds oxygen is very different in the near infrared than the absorption spectrum of deoxyhemoglobin. So you get an optical measurement of not only oxygen blood perfusion and blood supply, but also of oxygen delivery and oxygenation levels. So that is the key. The main challenges are due to the fact that in addition to this absorption, there is a high scattering of light in tissues. Orders of magnitude greater. So that's a measurement of the scattering coefficient, which is close to 10 inverse centimeters, while the absorption coefficient in tissues for typical concentrations of the chromophores is tenths of inverse centimeters. So this scattering is a major challenge, and it has been addressed over the years in a number of ways. But there's one additional challenge, and that is the fact that these chromophores are not distributed homogeneously. Of course, hemoglobin is in the bloodstream, so it's only in blood vessels. It is not uniformly distributed in tissue, and so for the other chromophores that are listed here. So that is a challenge for quantitative measurement, absolute measurements of these chromophores. But relative measurements are easier, and here I'm just going to show a couple of examples. This is a clinical application, this was a clinical study to show how oxygenation measurements performed optically with a conventional instrument were able to predict outcome of patients undergoing cardiac surgery. So these are the patients who had the oxygenation above a threshold of 50%, these are below 50%, and the mortality rate was greater in those patients with a lower oxygenation before surgery. So that's one of the clinical values of this measurement. This is another one. This is one of the abilities of this technique is to perform real-time monitoring, in this case at the cot site in a preterm infant in the first day of life. And this is so dopamine, a dopamine infusion was used to stabilize cerebral perfusion, but there was no feedback on this. And of course, this data, the oxygenation data was not used clinically to make any decision. But you see the potential value. Here there was a clear drop in this oxygenation level that was an indication that something was wrong. And it was realized eventually, the dopamine was restarted and stabilization was achieved. But this is one other example of how these non-invasive, safe, and real-time monitoring measurements can really have an impact in the clinic. But the emphasis here is on this oxyhemoglobin and deoxyhemoglobin. These are related to absolute measurements. In the case of functional near-infrared spectroscopy, which is a study of brain activation, the idea is to look for relative measurement, changes in the concentrations of oxy and deoxyhemoglobin. And this one here is the standard, well-established signature of brain activation as measured with non-invasive optical methods. So this gray shaded area over time, 20 seconds, is activation during visual stimulation. Measurements are done in the occipital region in the visual cortex. And the typical response is increase in the concentration of oxyhemoglobin and decrease, a smaller decrease in absolute value of deoxyhemoglobin. So that's a well-established signature of brain activation. And there is a Society of Functional Near-Infrared Spectroscopy that recently came up with a white paper to describe best practices for these kind of optical studies and how to report the data. But these are some of the key issues that were reported and are well established in the field. So the first one is how to interpret the physiological meaning of these hemodynamics that are measured non-invasively. The second is the importance of considering both oxy and deoxyhemoglobin. Functional MRI, which is the gold standard today for functional activation studies, is an extremely powerful technique. The one advantage, the one practical advantage that optical methods have is that they are truly sensitive to both oxy and deoxyhemoglobin, as opposed to the paramagnetic species in fMRI, which is deoxyhemoglobin. So the idea is to really take advantage of the information content of both dynamics of oxy and deoxyhemoglobin, and then we get into this in this talk. And the third one, as I mentioned before, is the potentially confounding contributions of extracerebral tissue. Your light has to travel through extracerebral tissue before reaching the brain. And how do you know how much of your signal is due to the brain and how much is due to scalp hemodynamics? So this is something I always like to show because I find it a very nice representation of functional near-infrared spectroscopy. This was a study we did a while ago, concurrent with functional magnetic resonance imaging. So that's the birthday code for functional MRI, and these black cables are the optical fibers used for optical imaging. This is how the optical fibers were placed. We know exactly where they are based on fiducial points on structural MRI, and this is the actual shape of the subject that was studied. These are the two detectors. These are the 8 sources, and then on the other side there are 2 more detectors and 8 more sources, so that this is the optically imaged area, and of course with fMRI you section the entire brain. That's such a powerful technique. And this is the measurement we did during finger tapping. So I don't know what happened to the hand. So the hand will be tapping. But this is the image obtained optically. This is the time trace for the concentration of oxyhemoglobin, and this is the typical signature. During finger tapping, the concentration of oxyhemoglobin goes up a few tenths of micromolar, and then after finger tapping is finished, there is a recovery. So that's the increase in concentration of oxyhemoglobin, and then there is a decrease in the concentration of deoxyhemoglobin during finger tapping. So now on the hand it's tapping, and these are the 20 seconds of brain tapping. This is decreased, as you see, by a smaller amount of the increase we saw before for oxyhemoglobin. But you see, the power of this technique is that it allows for real-time monitoring. Now, the key thing to notice is the typical time here. We're talking about a latency of the signal of a few seconds, because that's not how a brain works. Otherwise, this would make it for a very, very inefficient way of doing anything. You ask a question, it takes 2-3 seconds to process the question, 2-3 seconds to process the answer. There will be no baseball. So of course, we act much faster. If you see something as you're driving, it takes a tenth of a second for you to pull the brakes. So there is a communication between the electrical signals in neurons and the hemodynamic response, which is what we have access to. And also, the hemodynamic response is what functional MRI has access to. There are other techniques that have access to the electrical signals. But this is the kind of thing that can be measured with functional near-infrared spectroscopy, and the fact that it can be done non-invasively and continuously is clearly a major advantage. But the other advantage, as I mentioned before, is the ability to measure both oxy and deoxyhemoglobin concentration. So here I combine the traces, so the shaded area are the finger tapping periods, and here there is both the thin line is deoxyhemoglobin, thick line is oxyhemoglobin, okay, optically, and the point, the trace with the diamonds is the fMRI, the pole signal, the blood oxygenation level dependent signal from MRI. So the idea here is, can we take advantage, first of all, of both pieces of information from oxy and deoxyhemoglobin in optical measurements, but also, can we take advantage of the relative dynamics? Can we extract information from the relative dynamics of oxy and deoxyhemoglobin? So that was the emphasis on this technique, CHS, coherent hemodynamics spectroscopy, that was developed in my lab. The idea of looking at coherent signals, of course, is not new. It's used in any technique that uses transfer function analysis. In this particular area, has been used extensively in the field of transcranial Doppler to measure cerebral autoregulation in response to changing in arterial blood pressure. And this community also came up recently with a white paper about best practices for transfer function analysis of arterial blood pressure and Doppler flowmetry for cerebral autoregulation. So that was the background, but how to implement that in optical measurements of tissues. So this is actually a nice animation that someone at Tufts put together, and it's just a way to represent the vascular microcirculation in tissue. So there is an arterial compartment where fully oxygenated blood comes in, then there is the smaller arterioles and the capillaries where the oxygen exchange to tissue happens, and then there is a drainage to venous blood. So the idea here is to consider the microcirculation as a linear time invariant system, which by itself is an approximation, and consider the physiological changes, blood volume, blood flow, and oxygen consumption that are associated with brain activation, for example, as the input, and the concentrations of oxy and deoxyhemoglobin, which are measured optically, as the output. That is the idea. And so this is the, I'll start the animation because I think it's nice. So you have the red, fully oxygenated blood that gets to the smaller arterioles and capillaries. That's where oxygen exchange happens by diffusion to tissue, and then there is the drainage of blood. So the idea here is to introduce those few parameters, it's relatively few parameters that allow you to describe the optical signals. So some of them are related to the blood volumes in the arterial, capillary, and venous compartment, the concentration of hemoglobin in blood, about 2.3 millimolar, and the saturation of arterial blood, which, unless we are sick, is always 97, 98%. And then the dynamic parameters that are associated with blood flow, so the capillary transit time and the venous transit time of blood, and a rate constant for oxygen diffusion. So more or less that's all you need to relate physiological parameters of blood volume, blood flow, and oxygen consumption. So blood volume is here, blood flow is here, oxygen consumption is here, to the concentrations of oxygen and deoxyhemoglobin that are measured optically. So that was done, and one day I literally closed my door, students were knocking at the door, and I was developing the model. I was so happy with this model. Then I presented it at conferences, and I noticed, I did it 2 times, and that was enough. I saw the audience trying to stay awake. What are you talking about? So then I stopped. I'm not even showing the equations anymore. So I'm just going through the general concept. The general concept is that we need to have a known driving physiological process. That could be brain activation, or, as the case here, it could be an arterial blood pressure change. And the arterial blood pressure change, it happens spontaneously. As we breathe, our mean arterial pressure fluctuates with respiration. Or there is a method introduced in literature a while ago, which is inflating and deflating pneumatic cuffs on the thighs. That modulates blood pressure. And of course, we can control the frequency of modulation. So this is actually an actual measurement done on the subject in this protocol, where the arterial blood pressure is oscillating at the same frequency as the pneumatic cuffs that are applied. So that's a systemic change. It happens everywhere in the body. The question then is to see what is the impact of this systemic change in blood pressure in the brain. And that can be done by looking at the oxy and deoxyhemoglobin concentrations that are oscillating in the brain and that are measured with optical methods. So that is the idea. And by doing this, we can plot as a function of frequency, this in particular case 0.063 Hertz. So at that point, we can show the amplitude ratio and the phase difference of these oscillations in cerebral concentrations of oxy and deoxyhemoglobin. And the beauty of this is that now, because we are the ones inducing these oscillations, we can choose the frequency. So we can choose 0.063, but we can also introduce different frequencies. We can do the measurement at different frequencies. So now we have multiple data points in these diagrams. And then you go back to that model that could not keep people awake, where, however, now you can translate this dynamic behavior as a function of frequency to the physiological parameters. And so once you do that, you can perform a fit with those equations to that model. And from this fit, the fitting parameters give you information about the underlying properties of blood flow, blood volume, and oxygen consumption. So that is the basic idea of coherent hemodynamic spectroscopy. Now, talking about these oscillations of hemoglobin in the brain induced by these systemic changes in blood pressure, we performed a measurement at multiple distances. So this is the probe, the optical probe that was used. This is the probe on the forehead of the subject to look at the prefrontal cortex. There's one detector, optical fiber, and multiple illumination fibers ranging in distances from 11 to 40 millimeters. So that means that as you increase the distance, you're probing deeper and deeper into the brain, meaning that you're becoming more and more sensitive to the brain versus a superficial non-cerebral tissue. In this case, we performed 2 experiments to modulate blood pressure, the cuff inflation and deflation that I showed before, but also paced breathing. Breathing induces changes in mean arterial pressure, and again, paced breathing can be done, can be driven by metronome, and can be controlled in different frequencies. So the first thing I want to do, I want to just show what frequency domain interference spectroscopy is. That's what we're using. And in that case, the idea is that the power of the light source is modulated at a frequency that is on the order of 100 megahertz, so that the period is on the order of the mean time of flight of photons. And then if you illuminate with the power that goes on and off, then you're going to measure a signal with your detector a few centimeters away that is also modulated at the same frequency, but is phase shifted in response to the time of flight of these photons and also attenuated. So the amplitude and the phase of this detected signal is what is measured in frequency domain spectroscopy. And if you look at these two measurements, the amplitude and the phase of this photon density wave that is injected in the tissue, if you look at this as a function of distance, as a function of source detector separation, now you see the concept of these slopes that depend on the optical properties. All these different lines correspond to different optical properties of the tissue, and you see that the slope of these lines depends on the optical properties, and that is the basic idea of looking at slope. So going back to the experiment, this is what the experiment was about. On the top, there is systemic information. The very top is either the cyclic cuff inflation or the pace breathing at controlled periods. Here, there is the resulting oscillation in the systemic arterial blood pressure, both by cuff inflation and by pace breathing. And these are the oxy and the oxy. Oxy is always red, the oxy is always blue. That's because your veins look blue, your blood, oxygen in the blood is red. Measure with different methods. These are the single distance and slope methods. But here, this is where you can see the oscillations in the cerebral hemodynamics. So systemic driving, physiological process, and then cerebral measurement with optical methods. In this case, 0.1 hertz was the frequency. So here, the first thing we can get rid of immediately, regardless of whether the blood pressure oscillations are induced by the cuff or by pace breathing, the results are the same. So dashed lines, pace breathing, continuous line is blood pressure. So it doesn't matter what the driving mechanism to induce blood pressure oscillation is, the relationship with cerebral hemodynamics is the same. The main result, and we have seen this repeatedly on so many times over the years, is two. The first one, if you look at the amplitude ratio of the deoxy versus oxy hemoglobin oscillations, as you become more and more sensitive to the brain, this ratio increases. These purple lines are the one at a single distance, going at longer and longer distances. So that means that we will get more and more sensitivity to the brain. So the amplitude ratio becomes bigger, and the phase difference between the oxy and oxyhemoglobin oscillations moves from about in phase, 0 or 360 degrees, about in phase, to about in opposition of phase, closer to 180 degrees. And the question is, what does it mean? That's where that model of coherent hemodynamic spectroscopy comes into the picture. This is a slide that, to really explain everything that is here, and by the way, to get to all the points in this slide, it took years. I will spend the entire seminar, so I'll not do that. I just want to say two things. The first one is that we describe these oscillations of oxy and deoxyhemoglobin with phasors. Those of you who have seen phasors in your life, good for you. They are one of the most elegant ways to represent oscillations at a given frequency. They are used in physics, in optics, to look at diffraction, interference. Electrical engineering uses it extensively. Even fluorescence imaging now uses phasors. The point is that it's very simple. Any oscillations at any given frequency is characterized by two parameters, amplitude and phase. So you can represent a vector, which is called a phasor, with an amplitude and phase. And so the amplitude and phase of these phasors represent the oscillations. Once you set the frequency, that's all you need. The reason this is such an elegant and powerful and convenient method is that you can combine linearly oscillations at multiple frequencies just by vector sums of phasors. So that's why we use them so extensively. That's the first thing you want to say. We use phasors to to describe oscillations. And the second thing is the interpretation of these different amplitude ratio and phase difference of the oxyhemoglobin oscillations. So in a case in which blood flow and blood volume have comparable contributions, we go through steps which, again, I'm not going to describe here, and we find that the phase difference between oxy and deoxy is close to 180 degrees, so close to oppositional phase. In the case in which volume contributions dominate instead, by doing the same steps, you find a phase difference that is close to zero. The idea is that in scalp, this blood pressure is driving changes in blood volume. You're changing the pressure in your arteries, and in response, you have a big change in blood volume. In the brain is different. The brain is confined by a rigid structure of the skull. So these changes in blood volume are reduced, and now you have a dominant impact from blood flow. That's what coherent hemodynamic spectroscopy says, and that's exactly what we have seen in those measurements. As we increase the distance between source and detector, we become more and more sensitive to the brain. We go from this situation to this situation, and that's our interpretation. Okay, then the other technique, the dual slope technique. This really has to do with achieving preferential sensitivity to the brain in this non-invasive approach. The basic idea is, again, the fact that if you look at the amplitude of this photon density wave in frequency domain spectroscopy and phase as a function of distance, you measure slopes that are sensitive to the optical properties. The intercept of these lines is sensitive to everything else. Your source power, your efficiency of optical coupling between your fibers and tissue. Any drifts in instrumentation will impact the intercept, but not the slope. The slope is only sensitive to optical properties. So this was actually my first project as a postdoc when I arrived and went through the cultural shock of moving from Florence, Italy to Urbana-Champaign, Illinois. And so this is what we put together, this multi-distance measurement. That is something that also others worked on, and Hamamatsu developed this multi-distance system. This is a more recent application of multi-distance measurement to measure slopes. But all of these are what we now call single slopes. Slope measurement based on a single element, either a single detector or a single source. And then this is a brilliant idea, dual slopes. And I can say it's brilliant because it's not my idea. So Dennis Huber, he was the one who, back in the late 1990s, came with this idea, which really is brilliant. The idea is not to measure one single slope, but to measure two single slopes with given characteristics. So the idea is to sandwich two detectors with two sources, and then if you use one source and two detectors, you measure a single slope. So a slope based on a single element, the single source. And if you use the other source, source 2, you measure another single slope. The key thing is that detector 1 acts as a short distance measurement for the first single slope, and the same detector 1 acts as a long distance measurement for the second slope. So if your detector 1 is messing up because the detector changed sensitivity, then you see that instead of the theoretical slope that is based on the optical properties, now for single slope 1, you're going to measure something, a bigger signal, which is an artifact. It's only due to the detector being more sensitive. And so then you'll be off with the slope, and you have to figure out a way to calibrate this. But if you go to the second slope, that same detector is now the long distance detector. So if you increase the signal, now you're going to reduce the slope. So all you need to do is take the average of the two, and now you correct for any instrumental drift, any change in optical coupling. It's truly a powerful technique that does not require any calibration to perform accurate measurements. And if this didn't convince you, I think this should. This was just an experiment we did on a tissue like Phantom. Two sources, 1, 2, two detectors A, B. And we literally pushed back and pushed more or less on detector A to change the optical topic. The tissue is exactly the same. That pushing back and forth is going to mess up all of your single distance and single slope measurements. But once you take that dual slope approach, this has no impact anymore. So from a practical point of view, in real life measurements, this is extremely powerful. And this technique, over the years, took some time, but over the years, it has been recognized there are at least 2 commercial instruments, one in the US, one in Europe, that implement this approach, even though, especially in their case, it's impossible to understand how they use those data, but the configuration is exactly that one. But there is one more advantage of this technique, and now this is the one thing we have contributed over the past couple of years, 2, 3 years, and that has to do with the regional sensitivity. So if we look at a single source detector pair, single distance approach, this is the so-called banana regional sensitivity, the one on the logo, the one that in the field is commonly referred to as the photon banana. That's where your photons travels if you emit here and detect here. That's for the amplitude, and that's for the phase in frequency domain spectroscopy, and you see how the phase sensitivity is deeper. But still, you have this strong sensitivity to the superficial tissue. So think of this being the brain and this being scalp and skull. You still have this strong sensitivity to the scalp and skull. Once you implement that special configuration with the dual slope, with the 2 sources sandwiched in 2 detectors, now the regional sensitivity is completely different. Now it's more isolated and it's deeper. So now if you think of this early superficial layer to be scalp and skull, now you see that the concentration is more localized to the deeper plane, of course, we're interested in them. These, of course, are simulation on typical media, but the depth of maybe 12, 13 millimeters is comparable to the typical depth of the cortex from the surface. So this is banana regional sensitivity. We call this nut regional sensitivity. And so since then, in the group, we've been going crazy and say that now, finally, people in the field have the option of not going bananas, but going nuts. As you can imagine, we even published a paper with that title. And when I say this, I always like to acknowledge the fact that 2 researchers in Poland at about the same time, completely independent of us, came to the same conclusion, now in their case using kindly methods. So see, the 2 sources sandwiches, 2 detectors, and that's what we call the nut-shaped regional sensitivity for the first moment of the time of flight distribution, which is the mean time of flight, which is, to a very good approximation, the same thing as the phase that we measure in the frequency domain. So this is an experiment we did with this dual slope configuration. We do the same thing of coherent hemodynamic spectroscopy of inflating and deflating the cuff to modulate the arterial blood pressure. Up there again is the cuff oscillations, and in green is the induced oscillation in arterial blood pressure. And these are all of the optical measurement of cortical hemodynamics with single distance measurement, amplitude and phase, single slope and dual slopes. And the main result here is shown here. If we look at the relative, again, these are the phasors for, actually, these are the phasor ratios, so these are vectors of deoxy versus oxyhemoglobin. So they represent the amplitude ratio of deoxy versus oxyhemoglobin, and the phase is the phase difference between deoxy and oxyhemoglobin. And you see, once again, when we go from short distance in intensity to long distance, we're moving from 0 toward 180 degrees. And when we have the dual slope approach, more sensitive to the deeper tissue, we're getting even closer to 180 degrees. And phase measurements, the phase in the frequency domain that, as I mentioned already, is more sensitive to deeper tissue, even single distance phase measurements are now closer to the brain, out of phase oscillations of the oxyhemoglobin, and that's even further improved in dual slope. So our push in the field now is first to embrace frequency domain methods and to use phase information rather than intensity information to be more sensitive to the brain, and second, embrace this dual slope approach, which in addition to the advantage of being more selectively sensitive to the brain, it also has this huge practical advantage of not being sensitive to drifts, instrumental artifacts of optical amplification. And then the last topic I have is about dual slope imaging. So now how can we use now this dual slope approach for imaging? So far I mentioned this linear arrangement with the sources, sandwiches, and detector. In reality, you can use rectangular, trapezoid, rhomboid arrangements as long as you achieve that objective. That one detector has to be the short distance measurement for one single slope and the long distance measurement for the other. So this is one possible approach to doing things. We did a measurement on a dish like phantom where we had two inclusions, one shallower and one deeper. And the result is, yeah, those are some examples of dual slope methods. Yeah, that's a trapezoid arrangement, that's a linear arrangement. But this was the reconstruction we obtained for the images. So the dual slope intensity mostly was sensitive to the superficial structure. The dual slope phase was mostly sensitive to the deeper structure. So again, the idea is that this is skull, and this is brain. So that's why the dual slope phase, now this phase is the frequency domain phase, the phase of photodensity wave, is our approach. We then move on to design a number of dual slope source detector arrays. This is one of them, which has 16 illumination positions, 10 detectors, and it implements 30 dual slope sets that overlap significantly. And so in this case, we were able to implement this in practice because we have all of these illumination fibers, collection fibers, they're all placed in this probe that then is adapted to the tissue that wants to investigate. And one first application was on visual stimulation. So that's a source detector array, and that's a subject with the array placed on the occipital cortex, where the primary visual cortex is located, and that's the checkerboard pattern that is switched on and off to provide visual stimulation. This is a standard visual stimulation paradigm. So this is actually the protocol. It's a block protocol. The red periods are the activation periods. 8 Hertz is the frequency of switching this checkerboard pattern. And so yeah, it was 15 seconds of stimulation and 30 seconds of rest, periodically repeated. And the maps that are obtained are represented here. And so this is the single distance, the traditional single distance, one source, one detector with intensity and phase. These are the frequency domain phase. And once again, you see that the activation appears stronger in the phase, and our interpretation is that the phase, even the single distance phase, is more sensitive to the brain blood flow induced by activation. And when we go to dual slope intensity and phase, the signals are magnified. Both the intensity, when you go from single distance to dual slope, you have a stronger sensitivity. Same thing for phase, you have a stronger sensitivity. And this is probably more quantitatively represented here. If you just look at the pixel with the strongest application, that is the traditional signature brain activation that I showed at the very beginning when I described functional near first spectroscopy. Increase in oxyhemoglobin, smaller decrease in the oxyhemoglobin. That is visible in the single distance measurement at 37 millimeters. Once you apply the dual slope approach, now this signal is magnified. And again, our interpretation is that the dual slope gives a stronger sensitivity to the brain. When you look at phase measurement, again, this is the phase in the frequency domain. Now you see that even the single distance at the same distance, 37 millimeters, already gives a much larger sensitivity to brain hemodynamics than the intensity. And when you go to dual slope phase, you have an even larger sensitivity. And I think the very last slide I have is just to show an application we did on skeletal muscle as well. So this is the only application from brain applications. But we applied the same optical array to the calf of the subject during a venous occlusion on the thigh. So venous occlusion blocks the outflow, so inflow from arterial blood is still allowed, but then you block the outflow, and then you have an accumulation of blood. And this accumulation of blood has been used in the field to measure blood flow in the tissue. And so as we see what happens in real time, let me stop here. So you see what happens in the case of a dual slope intensity versus dual slope phase. Those are the only two things I'm representing, and that's for oxyhemoglobin and deoxyhemoglobin. There is a larger accumulation in this area of the tissue measured with dual slope intensity and dual slope phase. Now, we are really working on interpreting this. Our current interpretation is that the accumulation, the rate of accumulation of blood is greater in on the surface than on the deeper muscle. In this case, there's not the brain, it's muscle. And this is consistent with results reported in the literature. The other thing, of course, we have a map, and now we see a more uniform muscle hemodynamics as opposed to the skin hemodynamics that we see here. But I guess the point is that this adding the information of the phase with frequency domain spectroscopy and the dual slope with this arrangement of associated detector adds a new dimension to these non-invasive optical studies of tissues, both for the brain and for skeletal muscle. And I think this is where I am. Again, I give a big picture of the field, but I focused on two applications: coherent hemodynamic spectroscopy and dual slope methods in frequency domain and infrared spectroscopy. And I did mention that the push is to focus on phase measurements in the frequency domain versus intensity, and dual slope measurements versus single distance measurement for non-invasive studies of brain. And with that, many thanks to my group, the two lab members for proudly wearing the t-shirt from the lab. And these are current members. There's the book that Anne was mentioning, which was one of the most incredible experiences. In hindsight, I don't know what I was thinking when I agreed to do that, but in the end, it was a rewarding thing. And thank you very much for your attention.
Any questions?
So, great talk. This is very so, I know you, like towards the end, you're looking at the application for skeletal muscle, right? So, in theory, like, you think it would be promising to use this to see, to kind of quantify, like, the level, like, for peripheral arterial disease, right? Like, you know, obviously, like, a lot of the like, it's blocked and have these amputations, right? Do you think it would be promising to use this technique to kind of track the outcomes before and after intervention?
Yes, yeah, it would be, and in fact, peripheral arterial disease has been one of the target applications of the technique. Even the company that manufactures the frequency domain instrument identified that technique as the one to go after for FDA. And so, yes, this is absolutely yes. Actually, that is probably the technique, the application that makes the most sense for muscle study.
What company did you say was
The company?
Yeah.
It's ISS, which doesn't stand for anything. But you know that the International Space Station asked the company for the website, and they said no. we got that first.
So in one of the slides, you showed the finger tapping experiment. So you have to use multiple finger taps. I mean, you have to tap multiple times in order to trigger the hemodynamic response function, which you showed I wonder if that's feasible with just one finger stab.
So, yeah, it is actually. The one I showed, so that it's nicer, was actually the 14 average. But if you look at every single one, it was noisier, but you could very clearly see the signal. But of course it's a good question because it's a matter of signal to noise. In all laboratory experiments, the repeated paradigm is used. Also, we are using it especially for coherent hemodynamic spectroscopy because we want to have this oscillatory component. So I think the answer is that the technology allows for real-time, one-time measurements. And in fact, it is applied to methods where you don't have a periodic activation protocols. We are applying that on small kids in collaboration with a group that wants to develop coding in preschool and elementary school. So we take this little kid as they're asked to do coding, and we see in real time these signatures of increasing oxygen, decreasing deoxygen, and we are assigning them to rate activation. And that is done on a one-to-one basis. But it's true, the challenge there is signal to noise.
Great.
How are you able to conquer extracerebral factors such as malabsorption?
Can you be a little louder?
Yes, sir. So how are you able to account for any absorption by extracerebral factors such as like melanin for diffuse skin? Because I know you're looking at patients that they might not all have the same element concentration in shades.
Yeah, no, that's a good point. The advantage of functional immunotherapy spectroscopy is that it is only based on changes in concentrations. So from that point of view, melanin just acts as a filter. But of course, that becomes an issue when it's taken after absolute measurement. So as you know, with pulse oximetry, that becomes an issue.
What is the theoretical limit of the number of detectors and sensors, and so the theoretical limit of the spatial resolution that you'd be able to get?
That's a very good question. If I were to give a number, 5 millimeters, that is just a number thrown away. There are groups now that they have been developing what they call high-density diffuse optical tomography systems. They use a lot of sources and detectors. So they don't use any of the methods they talk, single distance to a slope. They use such a large array and they use full tomographic reconstruction methods. And I think they get to 3 to 5 millimeter resolution. Of course, the resolution depends on the depth. But the basic limitation is that those banana-shaped and even the nut-shaped regional sensitivity, they are on the centimeter scale. So you really need to have these high-density methods to improve on that. Otherwise, we're stuck with 1 centimeter.
I have a question. I saw that interesting geometry you showed towards the end. I know it looks very complex, but for dual slope, when you talk and you used it on subjects, you said that you need only 2 pairs. So is the source and detectors lighting turned on and turned off in such a way there's only 2 of them fired up, or how do you pick which are the best 2 combination of source and detector pairs to get your dual slope?
It's a very good question. I just realized I got to mention this important point. The detectors always are quite in parallel. Sources are always time multiplex, so only one source at a time. Another approach to frequency multiplex them, but still, you need to be able to tell from which source your signal is coming. And once you do that, then you can combine anything.
But they're not simultaneous.
They're not
And you
simultaneous.
pick the 2 best with the strongest.
Actually, we pick all of them. So all of them that meet our criteria for signal to noise and coherence when you do CHS. anyone is
And you
allowed.
can pick any two to give you the dual slope.
Yes,
And
exactly.
the second part question is, you move from brain, and one of the reasons you're doing the dual slope is because you have the skull, you have to go through the skull, and the sensitivity is gonna drop, especially in adults. When you move to calf muscles, there's no skull. What is the bigger driving need for a dual slope which cannot be achieved by a single slope? Because you're looking pretty much to the surface, and you don't have the thick skull to have the heavy scattering.
Yes, so that is true. The one thing that you still have in skeletal muscle is the lipid layer, which is still a few millimeters, of course, it depends on the subject. The other thing is to achieve some depth resolution, which of course with single distance you don't have. Single slope, if you have a layer structure like in skeletal muscle you do, there is really no conceptual difference between single slope and dual slope. However, there's the big advantage of the insensitivity to motion artifacts and instrumental bits in dual slope. That advantage.
So would it have an advantage when you talk of obese patients versus non-obese?
Sure, because
You're talking of another thicker layer.
exactly, that's one thing. And where we are now is really true, because even if you have a thicker lipid layer, the question still is, even in the dual slope measurements, how does that impact your measurement of the underlying hemodynamics? And we have some preliminary data, which in fact initially were confusing to us, where we have indications that that thickness of the top layer and most of the scattering properties of the top layer are going to impact the way we interpret the results.
If someone had a goal to map the brain activity during a subject, for example, having a seizure or during sleep, if you combine the dual slope technique with electrophysiology, essentially with scalp electrodes, what would be the spatial and temporal resolution of that?
Yeah, no, it's a great question. That, of course, has been done, combining EEG and even MEG, but EEG mostly with NIRS has been done. The temporal resolution is very different, but I would say that it's really the temporal characteristics of the signals that are very different. Because the temporal resolution is not a limiting factor for FNIRS. It's the fact that the hemodynamics signals happens over seconds, while EEG signal happens over milliseconds or tens or hundreds of milliseconds. So for temporal resolution, it is really just the nature of the signal. So there have been studies to relate the electrical evoked potentials to the corresponding hemodynamic response in order to study neurovascular coupling. Spatial resolution, that's where, in this case, spatial resolution intended as spatial localization. Optical methods, yeah, have the disadvantage of not covering the entire brain, but on the flip side, you know exactly which part of the cortex you're looking at. Electrical signals, you don't. So you have these signals come from a much broader area. So, but in case of evoked potentials, you know which is the target cortical area you're looking at. So I think the studies have been done anyways, and the emphasis has always been on the relationship between the evoked potentials and the hemodynamic response on different time scales.
Thank you.
Yeah.
And a second, to follow up on that, how sensitive the system would be for motion artifacts? Because during such activity, of course,
Exactly.
motion would be a significant.
That's one of the problems. So we collectively, the entire field has been looking at methods to correct for motion artifacts. Our argument is that the dual slope method already corrects for a significant part of these motion artifacts. However, they're still there. So usually motion artifacts happen so quickly that you can identify them on the temporal basis. Again, the hemodynamics happen much slower. Motion artifacts are usually faster. It's a spike or a sudden shift. So those can be easily fixed. But I would argue that those that happen more slowly, that are more challenging for these analytical data analysis methods, should really be addressed by the tool.
So just a follow-up question. So would you say that phase measurement is less sensitive to motion artifacts than intensity measurement?
Yes, less sensitive, not insensitive, but less sensitive, yes. Because phase measurements are essentially time of flight measurements.
Yeah.
And so they have much less sensitivity to motion artifacts that impact the optical coupling, for example. So, yeah, and we have seen that in actual data. We have seen more significant impact on intensity data than phase data.
Any other questions?
I see the benefit of using the phase modularity of the regularly for the last one you were showing the count of the count. Are you, and this is just a clarification kind of question, are you suggesting that that's not like a multimodal technique to use both intensity and phase? Because and again it's not a yes, I guess like when you measure the phase and the intensity, are you getting the same ecological information from what you have?
Yes, so the answer is yes. We are not saying that you should only use phase, because the intensity, even if it's more sensitive to the surface, still provides complementary information that help you interpret the phase data. So we are really after a combination of the two. And we are after the combination of the two for two reasons. One is to get better information about the spatial origin of the signal. Second, to improve signal-to-noise ratio. I didn't mention it here, but the challenge of phase measurements is signal-to-noise. Signal-to-noise is always worse in phase measurements than intensity measurements. So the idea of combining them to improve on the overall signal-to-noise is something we are exploring.
Any other questions? If not, let's go ahead and thank